So since we're dealing with enthalpy as a constant pressure thing, when we actually measure the heat changes or the enthalpy changes of reactions, we call that process calorimetry. Calor from heat, metry for measuring. And a constant pressure calorimeter would be, in this class, just a simple foam coffee cup with its lid on it to help keep as much heat in. You want to make it as insulating as possible. Usually, to make sure we have a really good insulating system, we use 2 cups. We just stack one inside the other. That extra layer of air helps insulate and keep the heat of the reaction inside the calorimeter instead of leaking out into the outside, into the surroundings. And then any temperature change, we can simply insert a thermometer through a hole we poke in the lid, and we can measure the temperature changes. And we just work on the assumption that all of the heat of reaction, all of the enthalpy change, stays inside the calorimeter, inside the coffee cups. The little tiny bit that does escape through the top or through the styrofoam walls is really negligible. So we can do all of our calculations based on that one assumption. So take a look at this sample problem. It looks really complicated, but break it down to its pieces. You're mixing 2 things together, doesn't really matter. There's a temperature change. Okay, immediately we know if there's a temperature change, we have to use our specific heat formula. S equals Q over M delta T. So we have to figure out the mass of the total water, and we've got that at the bottom, 100 milliliters at 1 gram per milliliter. Use density to find the mass. Stick that in the equation. We have a temperature change. Stick that in the equation. And we're trying to find the enthalpy change delta H. Now we know that delta H at a constant pressure system is equal to Q. So in the equation we can replace Q with delta H. And then we're just going to use a specific heat for water. It's a dilute solution. 1 molar hydrochloric acid, 1 molar sodium hydroxide is considered a dilute solution. So the specific heat of those solutions are going to be so close to the specific heat of water, 4.18, that we might as well just use 4.18. So go ahead and just use your S equals Q over M delta T, stick in your mass from the density, stick in your delta T from the problem, replace Q with delta H, put in the S, solve for delta H. We'll go over the answer to this in class. On the other hand, if we did constant volume calorimetry, where the pressure is allowed to build up, but the volume of the space doesn't change, that's called bomb calorimetry. Literally, bomb calorimetry. What you do is you take a sample that you're trying to test, and this is used a lot for finding calories in food. You compress it down into a pellet, and you weigh that pellet to a very precise amount, so you know exactly how much that weighs, or very precisely how that weighs. You put it inside the bomb, you screw the top on to tighten it, and it's steel reinforced, very tough, so when it blows up, it doesn't actually blow up. All of the explosion is contained inside the bomb. That's why it's constant volume. The volume doesn't change. Running into this container with the food pellet is a fuse, which is touching the pellet, and there's a little valve, and you pump somewhere around 8 or 9 atmospheres of oxygen, pure oxygen, into this thing. So there's far more oxygen than you would need to do the reaction. So oxygen is not the limiting reactant. The food pellet is the limiting reactant. Once it's submerged in water, you have the water being stirred constantly, so the heat's, so it's all flowing around. You put a thermometer in the water. You get the temperature of the water. You hit the button to detonate what's inside the bomb. You will hear nothing. You will see nothing, except the temperature of the water will start to rise. Because as that food pellet burned when it exploded, it released all that heat. Since the bomb itself is metal, it's going to push all the heat out into the water. It's exothermic. The water will heat up, the temperature will rise. You can measure the temperature change. And then doing a set of complex calculations, you can figure out from the specific heat of water, the specific heat of the metal that the bomb's made of, the specific heat of the calorimeter as a whole, the specific heat of oxygen and the other gases inside the bomb itself. You can put all that together and find out the total energy change when you combusted that food. And that is the calorie content of the food. Calorie is the American unit for energy, just like joules is. Joules is the SI, calories is American, just like miles and kilometers. We'll watch a video on this in class. So now we get to move on to Hess-s law, which is really the most useful law, practically useful law, in thermodynamics. First law of thermodynamics, yeah, that's very useful in a kind of a theoretical sense, but Hess-s law is really useful in terms of what we can do with it. And this uses the fact that enthalpy is a state function. It doesn't matter how many steps it takes to get from one place to another. It's always the same as long as you only consider the beginning and the end. Hess-s law uses that. And it says that if you're doing a series of reactions that starts with one thing and ends with another, final product, it doesn't matter how many steps or how many sub-reactions take place to get from the beginning to the end. When you add up all of those enthalpies, all those delta H's, you will get the same value as if you did that reaction in one step. This is why we can use that small table at the back of your book and calculate the delta H for literally hundreds or thousands of other reactions just by imagining that we did it in several steps, each of those steps being in that table somewhere. A few helpful hints. Start with your final overall reaction and work backwards from the smaller reactions to try to fit pieces of the smaller reactions in until you can make the final big reaction. If you need to reverse a reaction, go ahead and reverse the direction of the reaction. Just flop the sides. Remember, change the sign of delta H. And at the end, if you have the same thing on each side, if you have 3 O2s on the left and 3 O2s on the right, they cancel each other out, just like we've always been doing. So we can take a look at this sample problem. And this is a little on the complicated side to start with. It gets easier as you do more of these. You start to pick up the tricks. Just like balancing equations got to be a little tough at first. Once you figured out the pattern and the tricks to do it, it was okay. We have a combustion of carbon to carbon dioxide, so reacting C with O2 to make CO2, and the delta H is given. Combusting CO to CO2 is given. We can use those two values to figure out the enthalpy of combustion, or the heat change during combustion, of carbon to carbon monoxide. Now that one's not in your book, not in the table, but we can use the other two values that I'm given in the problem to do this. See if you can piece those together. Write out the reactions, see if you can flip reactions around or multiply them by certain numbers so that they add up to CO, or C plus O2 makes CO. Remember to balance it. We'll go over this in class.